All right, time to do some machine learning. By the way, can we all take like a minute to just stretch for a second? It's a pretty shitty day outside, and I'm feeling it. I'm feeling it. This is a requirement. All right, cool. Yeah. Earn your participation grade. All right. So, I've talked to a couple people about the homework, and some people are having a little bit of trouble with the math stuff, and if you aren't having trouble with the math stuff, that's good too. So today I'm going to be going over a little bit more in depth and piece by piece talking about this stuff. I'm also going to do some live coding, so get ready for me to struggle through that. Hopefully it won't be that bad, but we'll see. I think I know how to code. So let's start out by doing a little bit of recap. Tell our whole story again. So remember in the homework what we're up to. So we had our data. We all know this story, and we want to fit a line to it. Well, there's a bunch of different lines. So we come up with a loss function. Whatever we want. This is the MAE, just to keep drilling that home so you don't forget it. And we know that if we minimize the loss, we're maximizing the performance by whatever metric we come up with, because that is what loss is. And we know that different loss functions optimize different things. This will be more important in different homeworks. I know this is sort of supposed to be a recap for homework 1, but it'll be more important in other ones. And then we found out about this thing, the gradient of our loss function with respect to the parameters of our model being that line in this case. And we found out that taking a small step will necessarily decrease our loss, which is a really good thing to notice if we care about having better performance. And we came up with this little equation. We realized that there's a problem there. We could be taking too big a step. So we came up with this hyperparameter learning rate, which will scale the gradient and determine how big a step we take. Okay, cool. Recap done. So today I'm going to properly give you a training algorithm for SGD. And SGD being stochastic gradient descent, I'm going to clarify the difference between stochastic gradient descent and gradient descent real quick. So if we were to take our entire data set all at once and feed it in and get a loss over all of that, that would be our 1 over n summed over the difference of all the points, every single point in our data set. Then if we calculated our gradient and took a step, it would always be the same, right? There's only one possible step that we could take. It's the gradient over the entire data set. With stochastic gradient descent, instead of doing that, we're going to pick one data point. We can pick it randomly. We can find some sequence if we'd like, whatever we want. So we're going to pick some xi inside of x. We're going to update just using that one point. So it'll be like an xi/yi. So it's one data point. And what we're going to do, and that's what's stochastic about it, is that we're picking a random point. If you don't know what stochastic means, essentially involves randomness is the very hand-wavy way of saying stochastic. So we're first going to get our prediction from our model. That's the first thing we do. We set it in like this. And using our model that we've defined, so this is just generic to any model that we'd have, but the model that we have is this summation right here. So this is for every point. We're going to take every feature, multiply it by its corresponding weight, and then add a bias. That is what we had. This is also W transpose X. It's just the same exact thing, plus B. So these are the exact same thing. Again, I'm going to drill that home forever so you guys don't forget. That is what this is. Matrix multiplication is basically the same as a summation. Cool. Then we calculate our loss. This is, in our case, MSE, which we defined this way in the homework. Now, we didn't really define it this way, but we did. The reason that this isn't the same thing, so we have this summation over every data point, right? So we have this 1 over 2n here. I added the 2 for a reason you'll see later. And summated over every data point, the difference between them squared. The reason that this is the same thing that there is on the homework, which doesn't have that n or the summation, is the fact that we're doing stochastic gradient descent on every single data point one at a time. So in our case, when we come across this, n is equal to 1. We're looking at one data point at a time. There's no need to summate, and n is equal to 1. So this ends up being exactly the same as what we have on the homework. Anyway, that's why it looks like that. So then we update our weights using this formula that we have, and then we update our biases. A small note to people who might not have caught on to this nuance yet. The loss I, so I have a little I indicator of the loss. This is because every single data point that we put in will produce a different loss curve and a different gradient. So when I've been drawing it as a single loss curve that we're sort of hopping around, that's not actually an accurate depiction of what's happening. We really, every step we take, create a whole new loss curve. Now, if we didn't do stochastic gradient descent, if we just did regular gradient descent, that wouldn't happen because we're looking at every single data point every time. It's the same loss curve. But in our case, it is a different loss curve each time. So, small little nuance that is good to know, just in case you're wondering why someone might want to do stochastic gradient descent. Anyway, so we also know, so this is the whole algorithm. This is all it is. And we repeat this as much as we want, and then that's our model learning. But, yeah?
Is xi, is that like one instance of an entity, or is that a feature of an entity?
So, yeah, good question. So he's asking about the superscript, the in parentheses I. So, to remind you all again, the in parentheses I and the superscript, or in parentheses anything, is which data point it is. So in this case, we will have some number of data points, and each data point, regardless of how many features it has, will be an x with one superscript. So superscript I would be the ith piece of data. The subscript is the feature, which is used later on in this formula, the summation formula. Cool. So we also know what the gradient actually is, not in terms of like what it is in terms of numbers, but what it is symbolically. And what it is this. So the gradient of loss with respect to some value a, is generalizing it a little bit. We could also generalize the loss out, but you get the idea, is going to be the partial of loss with respect to every element of the a vector. So if we have some vector a, some list a, then we're going to find every single partial derivative with respect to each of those elements. Cool, not that bad. Like all this hopefully makes sense. Any questions on this? The algorithm? Cool? Cool. So how do we find the gradient? So first up, let's find the gradient. Let's start with this. So for each wi, we need to find, okay, I guess I didn't finish writing that. Anyway, but essentially for each wi, we need to first, for each loss, we need to calculate first the prediction, and then we need to take the prediction, compare it to the real value, and then we get the loss itself. So we do those two things, and what we find is that we can naturally break it down that way. First predict, then calculate the loss. We've been separating it that way this whole time. So it seems that if we want to calculate the derivative, that would also be a natural way to break it up. So we're going to do the derivative like so. So this is using the chain rule again. So we have that the prediction with respect to the weights, which is the first bit. We're using the weights to get the prediction. And then we have the loss with respect to the prediction, which is the second part, using the prediction to get our loss. So we're going to calculate those two values, just to sell you on the point of that's why we're calculating those two values in particular, and not necessarily drawing out an entire computation graph and doing everything. This is a sort of shorthand. This is how we're going to actually end up using computation graphs and using partial derivatives. Sorry if you wrote out the whole thing in the homework, and we're going to do that later and show you how it can be simplified. So let's start with the model. So this is our model. Nice. And let's draw the computation graph for it, very simply. So we're going to multiply them, each of these corresponding features, then add them together and add the bias. So that's the computation graph for this, pretty straightforward. And can everyone tell me, or can anyone tell me the values of these? So the partial derivative of y with respect to w1, the partial derivative of y with respect to w2, and the partial derivative of y with respect to b. Actually, I'm going to give everyone a second to think about it, just to make sure that they know the answer. And if you don't know the answer, then give it a think. All right, now.
Dy by dw1 is x1,
Hmm?
dy by dw2 is x2, and dy by db is 1.
Exactly right. So we can think about this by looking at our equation for our model. So this is not really using a computation graph in this point because it's a pretty simple function. So we look at it and we just take the derivative respect to w1. We see that the first term, we cancel out the w1, we get x1, and every other term we get 0. Same with w2. Then with bias, the same except there's not being multiplied by anything, so it becomes 1. All right, we're gonna generalize this a little bit later so that people feel comfortable with it. Cool. All right. The next part is doing the loss. So this is our function MSE. But like I said before, we're going to assume that n equals 1 because we're doing stochastic gradient descent, at least in the homework, at least in this homework. In future homeworks, we might be doing something different, so keep that n in mind. But for right now, we're going to remove it. And we can just draw a computation graph like so. So that's it. And then with that computation graph, we can see that it's a pretty simple operation, actually. And we end up getting that our derivative of loss with respect to y prime, or the prediction, is just going to be that. So this is the formula for our MSE. So I just removed the 1 over n in the summation, dy. So can anyone tell me what the derivative there is? I know that some of you have submitted the homework, so some of you have got to know. I'm going to pick someone else, sorry. Yeah.
It would be 1/2 times y minus y prime times -1.
Very close. It's actually 2 times because it's going to be, we're squaring it, so we move it down. Yeah, exactly. And one thing to note here is that when we're moving it down, we're actually getting the minus. So it's times -1 because inside of the parentheses, we have minus y prime. So we're subtracting that, which means we have to end up with a subtraction on the outside. Cool. That's a little thing that might trip you up if you miss it, but there it is. Cool. So now let's push those things together and come up with a final answer here. So that's our computation graph for our model. And then we have our loss function, so we'll tack that on. So we just tack that on, and now we have our loss with respect to all of our inputs and all of our weights. Cool. This is our full computation graph. And now we know what we want to calculate is just those 2 values. Anyone want to give me an answer to either of these? Actually, talk in your groups for a couple minutes just and come up with what those values should be. All right, all right. Yeah, I know that some people aren't done yet. I'm going to call it there though, so we can talk about it a little bit. So, can someone tell me what these derivatives are equal to? How about this? Can anyone tell me what these derivatives are equal to with respect to the things we've already calculated, to the derivatives we've already calculated? Yeah.
I will concentrate the whole answer.
Let's go with the first question first, or the question I just asked first.
It would be partial derivative of L with respect to y dash times y dash with respect to W1.
So that's exactly right. So using chain rule and everything that we know, so we're going to use the chain rule from a couple slides back where I said it was a natural split. And we know that this derivative is going to be equal to the partial of loss with respect to y prime. So that would be loss with respect to prediction times the derivative of prediction with respect to W1. So those two values we've already calculated. We don't need to do it again. We just need to multiply them together. So what we had was that the first was going to be equal to, the first in this case was going to be equal to 2 times, or negative 2 times y minus y prime. And then the second was going to be equal to x1. So there are two values that we just calculated, and we're just going to multiply them together. It's beautiful. It's very simple. And that gives us
Minus 2y minus y prime times x1.
exactly. You just multiply them together. I wanted to give you the glory, though. So that gives us these two answers. So for the first one, it's times x1. And then we find that since we're doing the same operation on every single one of our w's, we actually get that it's the same thing. So we get the same thing, except now it's x2. So that's the only difference between them. You see that they sort of come together, and then every operation since then is going to be the same. So we are going to multiply the same first bit, and the only thing that changes is what happens after the split. It's a little bit of a intuition that you can get that will make this sort of thing pretty easy. Cool. So, real quick question. What would happen if I changed the loss function so that instead of being y minus y prime, it was y prime minus y squared? So what would happen? Yeah? It'd become positive. Kind of correct. The reason I say kind of is that this negative 2 would become 2, but do you want to say something?
It would just change sign.
So it would change sign, except it wouldn't. This is the tricky thing. So it would actually change sign here to be 2 times y minus y prime, but if we distribute the negative sign, it ends up being exactly the same. There's a little bit of tricky nuance here, but it does actually end up being the same. There are cases when it doesn't, so you have to be careful. But in this case, it does. So just a little bit of a trick for you. Neat. So now I tried to introduce this notation a bunch of times, but I'm going to do it again. This notation where we have this model, but we're going to write it as a matrix multiplication. So I'd like you all just to take my word for it at this point. We're going to have some vectors that we can turn this computation graph into, and it's very natural for us to do, turn this computation graph into this. Just some vector x and some vector y dot producted together. So that's exactly the same as doing w transpose x is the exact same as w dot product x. All right? So from now on, when we see a computation graph and this operation is happening, we're going to use a dot product instead of this whole notation. And we've already solved what the partial derivative is to both of them, so let's look at what we can do. So before we said that for any particular w1, so dy dw1 is equal to x1, and some wi has a similar thing where it's just every single one of those. What we find now is that we can actually just write it as dy dw and just have that be x. So this is the entire derivative. Instead of doing each piece, we're just doing it as a vector. And this is a really useful thing. You can see, for one, it's much simpler. We have no subscripts anymore. It's very nice. And we're also calculating all of the derivatives at the same time. No need for a for loop or anything like that. If you have any of those in your homework, if you have any for loops at all, You should probably remove them because in the next homework that'll be too slow. We also have that this is now a known thing that we have. It's called matrix calculus. Ooh, scary. This is the only thing that we're actually going to keep in our minds, which is when we have W transpose X dW, that is going to be equal to X. We know it now. We can use it in the future. And so we don't need to draw out that whole computation graph and recalculate out that this is X. I'll be going over this again in a second, just to make sure that this really lands home and why this is true lands home. But for now, just accept that, and you can use it now from now on. It's very good, very useful. Cool. So I want to try something. I'm going to try doing math out by hand on this, using this little thing, and make sure that everyone gets it so you can see all of the steps that are required to do all this. I know I just kind of did that, but I want to be able to go over a couple other small points. So let me swap this over. By the way, are people feeling comfortable with this math? Thumbs up or thumbs down, I guess. Okay, that's good. Goodish, I don't know. Maybe it's unnecessary, we'll see. But it didn't change it, huh? There it goes. Okay. So, first up, I want to talk about one thing that a lot of people have had questions about, which is essentially that our model ends up being f of x equals the summation for all of these I to whatever, to m I've been saying, of x, I, w, I, and then plus b. And a lot of people have been worried, oh, how legible is that? That's not super legible, is it? All right, I'll write it bigger. Summation xi, wi, plus b. All right, we've had some fx equals this, where I is going up to m. It's all the features. And people have been concerned by doing this, dwi. So, or dwj, I'll say, for the sake of it, so that they're not I. So, I'm going to show you why it's very natural that we're getting the answer we get without using a computation graph and all that, just to show you. I did kind of hint at this earlier, but if we expand this out, we get exactly x0, w0 plus x1, w1 plus all the way up to xj, wj plus, and then eventually our bias. And just using the calculus rules that I'm sure you're all familiar with, I mean, it is a requirement for this class, so I assume you are. We know that if we take the derivative of all of this with respect to some wj, that's the same as taking the derivative of each of these terms and then adding them together. So if we take the derivative of the first term with respect to wj, so it's just this first term, what do we get? Someone said over here, 0. So this is the main intuition and main mess up that people have with this. W0 and wj are not related to each other. They are different variables. So when we take the derivative of this with respect to wj, we end up with 0. There's essentially two separate variables that are being derived by a different variable, and that is always going to be 0. So we get 0 for all of these, but then once we hit xj, wj, what do we get? xj, exactly. And then we get 0 again. So when we summate all these together, we just get xj. There you go. I hope I've convinced you of that point. I hope that's good. Are people benefiting at all from the handwritten math? Yeah? Okay. I'll keep it going. So now let's do the loss function. So this we now have is going to be equal to dy prime. So this is y hat dwj. And as a reminder, when we're doing a derivative with respect to a vector, so what we're immediately going to want to do is do dy hat dw. So we're doing it with respect to a vector. In the same way, with the loss gradient, it is with every single term. We get the exact same thing here. Yeah?
So is y hat equal to f of x in this situation?
Yes. So anytime, so I use three things interchangeably in this class for different reasons, and I'll explain each of them. So one, I say f of wx, right? That is going to be the same as y prime is going to be the same as y hat. All three of those things are exactly the same thing. They are different for the following reason. One, getting y hat on these slides is really difficult, but y hat is a better notation, so I want to use it in the homeworks. Two, f(w) of x is going to be a general form for other tasks. When we have y prime, it's assumed that that is a prediction of either a class or of a regression task. But in the future, we won't necessarily be actually predicting anything. So we want to have a general form, which is this f(w) of x. So they are all the same thing. I know it's slightly confusing, but I believe in you. I try to color code them so you can tell that they're always the same, but I don't always do it. Okay, cool. So what we find is that when we do a derivative with respect to a vector, this will always be a vector of the same size as what we're taking a derivative of, first off. And essentially all it is we're going to take a vector where we take the derivative of the first term, and we do that for every single term. So this will just be dy hat with respect to every single one of the dw's. So when you're going through and you're doing the homework, or dm, I guess, is actually what it is, you want to make sure that when you take the derivative of when you're calculating the gradient of the weights, you want to make sure that it is the same size as the weights themselves. A simple way to justify this idea is that we are subtracting them from the weights. We want them to line up. If we had a single value, I guess maybe it's okay, but it doesn't make sense for it to be a different size vector. In fact, we want to have each of the weights update independently, so we need a vector to update them. Cool? Cool? All right, nice, nice. Next up, we're going to look at the loss function. So again, we've sort of done it out, but I still want to go over it again, which is we have this 1/2 y minus y hat, and as we know now, it doesn't actually matter which way we do the subtraction. It matters for you coding because you might make a mistake doing the subtraction sign, so keep an eye on it, but it always ends up being the same value. And we want to do this, and we want to find the loss function, so this is L. We would find the loss function with respect to y hat. Right? So again, in here, it's really a straightforward bit of calculus. There isn't much need for us to use a computation graph or anything. There are reasons to use a computation graph, as I hope I have convinced you of doing the batch norm on the quiz. But on these simpler problems, do whatever is easiest for you. I want to make that clear because I've heard a lot of people struggling with the computation graphs. The computation graphs are there as a tool, not as a requirement. If you can do this calculus without them, you don't need them. If you can't do the calculus without them, use them. Okay? Cool. And of course, we do the calculus that we just did, and we get -2 y minus y hat. Cool. Very nice. And then lastly, all we need to do to put them together is say that we want to find this right here, wj even. We care about this. We care about with respect to just w. Yeah?
Did you drop your 1/2?
Oh yeah, I did. Here you go. There you go. Beautiful, beautiful. So yeah, that's why we had the 1/2 there. By the way, if you hadn't picked up on that yet, when the 2 comes out and we want to replace 1/2, it is purely there to make our lives easier. And you might even notice that if we kept it there, it's just scaling our gradient. So we would just change our learning rate. It's something we're already controlling, so it doesn't matter whether it's there or not. I could multiply this by 1,000,000. Doesn't matter. It's still correct. So this, and again, we just have, as we said before, we can take this and just do the chain rule on it. And I really want you all to get familiar and comfortable with the idea that in cases like this, chain rule really does work the way you would expect it to if it was fractions. We can just cross these out and we get the correct answer. But at this point, we already know these values, so we can just plug them in, and we get that this is minus y prime, and this is xj, and that is exactly equal to what we want it to be. We don't need any more equals. So We can talk about the dimensions of this also. So I have said before that we can have multiple dimensions to everything. So this y could be multidimensional, but we know we'll always have that y prime is the exact same dimension, so it generally will only have a length. Right? So it could be a vector, in which case this would be a vector of the same size, in which case this would end up working out. Okay, maybe I'll save the dimensional talk for when we're actually doing multi-layer perceptrons, which is going to be next class. For now, just accept this. This is how we do it in the homework 1, and I want you to be able to fully get this. So everyone got it 100%? Yeah.
Would this negative also show up when the y hat is first?
Yeah, so what happens is that this is exactly equal to, if we just swap this, right? So if we distribute the negative sign, then we get that this is y hat minus y times xj. If we were to swap this around so that this was instead y hat minus y squared, then we don't get the minus sign here because we'll just get 2 y hat minus y, and then this is multiplied by this inside, y hat minus y d this dy hat, which happens to equal to 1. So this doesn't end up with a negative sign, actually. But if we distribute the negative sign down here, we get the exact same answer, you'll see. Yeah?
Just to clarify, are these outside the summation, right?
Yes, it is. So b is outside the summation. Yeah. Cool. All right. Everyone happy with this? Everyone happy with this? Cool. All right. So that is the math, and now we get to do something a little bit more scary for me, but maybe a little bit more useful for all of you, which is some live coding. Doing them back to back, I know, right? So this one will probably be more helpful to everyone, and I also want a lot of questions about this. So I'm going to be trying to be inclusive of people who don't know Python and people who don't know NumPy, which would probably be a good chunk of the class. And I want to, one, justify why we're using NumPy at all, and also I want to help you guys learn a little bit of the convention of how we code neural networks and how we code with NumPy. All right, cool. So these slides are also up on Moodle and on Piazza. So if you want to follow along with this and look at the code yourself, you can. If you want to also just play around with it, you can too. So I'm using here a Google Colab notebook, which you may have used or may not have used. Essentially, it's just a Python command line with little blocks, so you can run each block one at a time. They're very nice, but I don't use them when I'm doing more production code, but they are very nice for things like this. Some people really like them. They're good sometimes for research too. So this is just installing 2 libraries. This is NumPy and Matplotlib. NumPy is the one that we're going to be using that is super amazing and great, and everyone should use it all the time. And Matplotlib is just for plotting, as you might imagine from the name. You just need this to install them. You're going to be running those commands on your computer, so cool, if you haven't done it yet. Then I'm just importing all of them. Cool, really straightforward. This is how you do imports in Python, in case you haven't seen Python before. Just import them, and if you want a particular function from a library, for example, in this case, I want the time function or method from the time library, which is kind of a confusing example in this case. But if I just imported time, I would need to use time.time to call that method. Instead, I'm going to just be able to call time. Anyway, that's used for timing, by the way. So our first question here is, using Python, we want to initialize an m-size array with values between 0 and 1. Okay? So anyone have any suggestions of how we go about doing that? Just a little bit of Python, simple Python convention, or make it simple. Don't give me a in bracket thing. Yeah.
Just array with 0 times m.
Array with 0 times m. So I'm not sure exactly what you are suggesting.
Like a single array with 0 inside it times m, it would make array of m dimension with all zeros.
Yeah, so we want it between 0 and 1, though, like randomly between 0 and 1. So I'm actually explicitly saying that we want to use this function right here, random.uniform. So that gives you a uniform number between 0 and 1. We're not going to, in this class, very often touch upon the statistics of all of this. But this is, in general, how you want to initialize your weights for a couple reasons. There are other ways to initialize them, but generally we're going to try to initialize them uniformly over 0 and 1, or normal distribution centered around 1. But here, I'll do a very simple thing. So first off, I'm going to do a for loop. So this is a little bit of Python. Again, if you aren't really comfortable with Python, this is how for loops are written, and this is a nice little trick to know. So we have some size m that we care about. So we can say for I in range m, and that will go up from 0 to 1 less than m, whatever it is. Is it hard to see, by the way? I see some people squinting. Okay. I'll go one bigger for now. All right. And then all we could do in here is we can say r1.append. So this will just stick on something at the end of the array, and we'll just append a random.uniform, and then so 0, 1. So this will go uniform between 0 and 1. So this is just appending onto the list. You won't really in this class ever need to use lists. Won't need to. You can if you want to, I suppose, but not in any of the neural network stuff. If you use it in the neural network stuff, it'll be way too slow, as we'll see in a minute. And then we can do the same thing for the last one, for the other array. So here's how we would initialize two arrays. Okay, fine. So here's how we would initialize two arrays. Cool. All right, everyone. Anyone have any issues with this? This is pretty straightforward code, so hopefully you guys are good with that. Cool. So next up, we get to initialize with NumPy. And some of you might notice a little secret here, which is I'm basically giving you the entire homework answers. So hopefully that's helpful. I'm not telling you explicitly any of the answers besides, I guess, the math part. But you can use everything here that's in this notebook to put together to do, it will give you every single piece that you need to be able to do the homework. So if you're having a lot of trouble with the coding on the homework, I'm probably not going to do this as much with the later homeworks, but in this homework I want to be able to give you the tools where you don't need to go look online. You should have them all right here. Okay, so in this case, if we're trying to do something so we're just trying to return in the range of 0 and 1, we have a nice option in NumPy. So we're going to call it as NumP, by the way, or NP, by the way. I do the same thing in the homework. So I saw a couple of people who were trying to use NumPy. I'm importing as NP up here at the top. So that means when I'm calling the library, I call NP instead of NumPy. I don't know why that is totally convention, but I've never seen it used a different way. So people always use NP. Cool. So in here, just do np.random.rand and then the size. And this will give you exactly the size that you need. And this will do exactly what we want it to. So this, for one, I just want you to notice that it's very easy to initialize NumPy arrays pretty much however you want, as long as you know the sizes that they are. And you also must define the sizes whenever you make a NumPy array. Essentially what NumPy is it is a C library for like arrays and array multiplications that has been imported into Python. So anytime you're going to be making these arrays, I don't know how familiar people are with C, but we need to essentially follow those conventions of always knowing the size and the type beforehand. So in this case, we know that it's going to be float values, and we know the size of it is going to be m. That's just what random.rand gives you, actually. So again, like I said, that it's sort of the convention to have our arrays initialized between 0 and 1. NP knows that. NumPy knows that. And so everything is very built around what we need for machine learning, which is why it's so useful here. But yeah, this is what this function random.rand does is give us between 0 and 1, which is very nice. And we can do the same for this one. Cool. And so this should work. Cool. And now what we want to do is we want to do multiplications. So with the Python array, we're going to just do something very similar to what we did before. We're just going to do a for loop. So we're just going to do for I in range m, or in range length of R1. So that's, again, a little like thing you can do. that will iterate over all of the indices of that array, which is nice. You can do it different ways too, but that's how I tend to do it just because it's quick. And then we're just going to say, we're going to define some output array, output equals whatever, and then we're going to, in here, output.append R1I times R2I. Cool. So this should just multiply each value. So this is doing a dot product like we were doing before, but it's doing it manually where we're just looping. This is just about the fastest way to do it in Python. So this is our limit for how fast we can do it in Python, just about, not using a different library. So that's cool. With this one, though, we're just doing a dot product. So we're doing a dot product in NumPy, and we're doing a dot product in NumPy. What we can do is just np r1 dot dot. So that is doing a dot product. It's beautiful and very nice for us. Again, everything in this library is built for use with machine learning in mind, so everything is very clean and easy for us to do. So doing a dot product. There you go. And that's about as quick as you can do it there. So now that's more or less the coding I'm going to do here, but now I want to do a demonstration. So what this is going to do is it's going to time both. So it's going to time the initialization and multiplication of each of these. First the Python, and then it's going to do the NumPy. It's record all the values and then output them. So I'm going to go over all of these values, and I'm going to do that same thing. I'm going to test the timings of each of them. About how much faster do people think NumPy is going to be? So all we're doing is just a very, very simple operation. Yeah, some people saw it. We're doing a very, very, very simple operation, right? We're just multiplying our matrices here. This is the fundamental thing that we are going to be doing in machine learning the most, is just dot products. All right, so in these sizes, about how fast do people think it's going to be? Just someone shout out some numbers. 100 times faster? Nice. And we're going to go with like 1 trillion times faster. Huh? 1,000. Cool. I think that about covers it. It is going to be faster, but we'll see how it scales, and we'll see really why this matters. So we're trying it over these, and you can see how quickly it goes. And you see that for size 1, NumPy is actually a little bit slower for size 1. For size 2, it looks like NumPy, again, is a little bit slower. For size 100, now NumPy is significantly faster. Then for size 1,000, NumPy is a little bit slower. And then for 10,000, NumPy is a good amount faster. And then for 100,000, NumPy is a lot faster. And something I want to point out about this is that these sizes, and I will now graph it for you. You can see how to use PyPlot here. So look at that. I think this should be pretty compelling as to why we use NumPy. Its major factor is not that it can do these very simple operations quickly, it's that it scales extremely well. And not only does it scale extremely well on doing this dot product, but it scales extremely well on doing any operations with these arrays whatsoever. And generally, we don't just have a single vector that is multiplying by a single vector. We generally have 2D matrices multiplying against 2D matrices. Sometimes, in machine learning, and later in this class you're going to see, we will even have 4-dimensional matrices multiplying against 4-dimensional matrices with tens of thousands, hundreds of thousands of values. And when we compare those, our NumPy is going to make not only it a lot faster, it'll make it feasible. Trying to do it with for loops, trying to do all this will, 1, be a huge pain in the ass to code, and 2, won't run until the end of the universe. So we need to use NumPy for these things, otherwise we won't be able to run them. So it's really important that you learn how to use NumPy. Hopefully I've demonstrated that. And hopefully I've demonstrated that it's actually not that difficult to use either. All right, does anyone have any questions about NumPy? No? Yeah.
So is the difference is just like computing it outright instead of doing loops?
So sort of. It's not exactly. So basically, it uses every computational trick under the sun to make these things faster. For example, when it does a matrix multiplication between two large matrices, it doesn't actually just multiply the matrices. It uses like eigenvectors, eigenvalues, all that fun linear algebra stuff to be able to do this very fast. Same goes for inverse. There's actually some really interesting algorithms to do these things really quickly. And essentially, when you're coding in Python, you are trying to compete yourself against these brilliant algorithms that can run in very good time. And you can imagine when you have many matrices, like if you have an n by n by n by n matrix, you now have an n to the fourth times n to the fourth runtime thing that looks really bad. And these are much, much faster. Yeah. Cool. Yeah. So now I want to talk about a couple operations just so you guys have a good sense of like how to use these. So this is just initializing two arrays that we have here. Nice. Just going to initialize them. If you do it again, it'll be, again, random values. Cool. So I guess it's sort of spoiling it does down here. I erased them all beforehand. I guess they pop back up, though. Anyway, if we multiply them together, if we just use a multiplication symbol, it doesn't do what we're doing before. That's why we're using the dot product. If we multiply, it'll just do an element-wise multiplication. So we have these two values, and it'll just multiply them each down the row, and it'll end up with the same size array. What we want to do instead, as we saw before, is to do the first array, so npr1 dot npr2. And this will do exactly what we want it to, and we'll calculate that single dot product value. As a nice little aside, all of these ones where you have the dot, like you use one of these arrays and then dot something, you can actually do it as np dot dot. So now we're calling np, which is the whole library, and then we have the arrays in here. And then that works exactly the same way. You can, in fact, have an extra argument in it that will assign the value to one of the other arrays. So you can also do that if you want to. Just to like see how each of these operations work, just so you can see them. So if we have npr1 minus npr2, this will work exactly the same way as multiplication, but it will be a subtraction, right? Anyone want to try any other operations and see how they behave? Anyone have any good ones? Yeah? What? Dividing? Yeah, I think you can predict where that's going. Yeah, it's element-wise prediction. One thing that you might not 100% know is if we square it. So if we use Pythonic squaring, this is how you square stuff in Python, by the way. You can raise it to whatever power you want. Sure. This will actually be element-wise, so that's not necessarily a natural option for it. It could be that we are like dot producting these together. And you're going to need to be careful with this operation because when we go to higher dimensions, it won't actually necessarily work that way. So just be careful with that one. We also have a couple other things that I just want to show you how to do in NumPy because they can be important. So slicing is just when we have some array like this. Right? So if we look at our array, we have 5 different values. If we want to get some subset of it, we can use indexing like we had before. And we can say, for example, there, we'll have us just return the final 3 values. Or we can say the first 3 values by putting on the other side of it. Wonderful. Or this is going to be up to 3, which is going to be 0 and 1. So we can do that, or we can do something like -1 is going to return the last element of the array. Very nice. And it's going to return it not as an array anymore. It's going to return it as just a float value. So all these are just little things that I want you to have under your belt. I know that you're all adults. You can go Google your own stuff, but I want them to be here so you can see them. And that's basically it there. And then I'm going to talk about transposing, which is just changing the dimensions of it. So this is something that I know that some people were not as familiar with. Looks like this thing turned off. I don't know why. But when we're transposing an array, all we're doing is we're swapping its dimensions, like I said before. So if we have an A by B matrix, and we transpose it, we'll end up with a B by A matrix where every single element that was at some some like CD index, so is at the cth, dth index, then it will change to the dcth. I guess I'll maybe use this to do it. This will be a little bit clearer. All right. So just to do this. So if we had some array like this, yeah, we'll have, say, A00, A01, A10, and A11, right? So let's say that this is our matrix. If we take the transpose of it, it's just flipping it over the diagonal. So A transpose is just going to be A00 and A11 are going to stay the same, but then these two are going to swap. Cool, cool. Everyone feel okay with that? Cool, cool. When you get to higher dimensions, it is a little bit trickier, but basically the same principle applies. Cool. All right. So now I want to look at, so to do transpose, all you have to do is take some array, and you can do dot .t. You can also do dot transpose if you want, but this is very nice. Just dot capital T will do the transpose. One thing you'll notice, though, is that when we're doing a vector like this, we'll actually end up with it not swapping anything because it's a one-dimensional vector. So all this time that I've sort of been saying that it's doing a transpose, we are doing a transpose, don't you worry. But when we're doing the transpose with a single vector like we are in the homework, this actually wouldn't work. So this would be doing times NPR1, for example. So these two are the same size, and what we'd like to come out is a dot product of the two, which has a single value. But if we do it like this, we'll actually end up still with a vector. So if you have been listening to me a little bit too much during these lectures, and I've been saying transpose, 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 when we do vectors, it actually doesn't work just because of a nuance of this. If we were to initialize our vectors a little bit differently, it would actually still work. We would need to essentially initialize it with an empty dimension, but that's a little bit unnecessary. So instead, when we're doing single vectors, we're going to use a dot product just to get everyone on the same page. Cool. And then as a little bit of a teaser for what we're doing in the next homework, we can also initialize multi-dimensional matrices. So doing this, we'll initialize a matrix that is a 4 by 5. That is 4 being the rows, 5 being the columns, just so you know. And then we're going to initialize a 5 by 1. So first off, let's just initialize them. And now, out of curiosity, what do people think would happen if I tried to multiply these together? A 4 by 1? Let's see. So if I do R1 times R2, who else thinks it's going to be a 4 by 1 matrix? Yeah? That'd make a lot of sense, right? How about it doesn't work? So we can actually see, R1, sorry, but it still doesn't work. So I did double R's instead. So it still doesn't work because these shapes cannot be broadcast together. That's because this operation, the multiplication operation, is trying to multiply them element-wise. So it's trying to multiply them in place, essentially, where it's saying the first dimension is going to match, and I'm going to multiply all those together. So like we had before, it's an element-wise operation. Element-wise operations are going to assume that your values are the same size, or at least can be, as it says here, broadcast together, which means that you can change the shape in a natural way. If this was, for example, let's take the transpose of it. So if we take the transpose of it instead, that will now be a 5 by 4 matrix being multiplied by a 5 by 1 matrix. And it can do this element-wise by essentially changing the 5 by 1 into a 5 by 4 by duplicating the values. So now if we do it, we'll end up with some matrix that, as it turns out, is going to be a 5 by 4. Weird, huh? So these sorts of things are going to trip you up quite a bit when it comes to doing the second homework, probably, because we're going to be doing a little bit of this. What I'm going to suggest is to just always be aware of the shapes of the matrices that you're dealing with. If you want to check those, you can always just do your matrix dot shape. That's a NumPy thing. It'll tell you the shape of it. So if we want to do the transpose, .transpose.shape, it'll show us that is in fact a 5x4. So now if we try to do something like this by R2, what do people think will happen? So right now we have a 5x4 matrix and a 5x1 matrix. What happens if I try to dot product them together? Any thoughts? Will it work? Thumbs up or thumbs down? Will it work? Yeah, you're gonna get to do a lot of this testing on your own probably. But let's see. It does. Huh. Not only that, it's a 4x1, huh? So this shows that the way that the dot product is going to work is essentially that we're going to be doing the matrix multiplication that we've talked about. A dot product is a matrix multiplication and is also a transpose multiplication. So this is exactly what we get out of it, where we just line up the dimensions. A dot product should be thought of always as a matrix multiplication. So we're multiplying first matrix by the next matrix, and that's how the dimensions line up. Cool? So anytime we're looking at how the dimensions are and how to line them up, a dot product is a basic version of that, and there are different operations that come into play here. Now, how about this? Let's say that we have what will happen here? Anyone have any guesses? What shape will come out of that? Yeah?
4x5x1.
4x5x1. Anyone else think 4x5x1? Yeah? You do? All right, let's find out together. No, sorry, it doesn't work. So yeah, they still need to match in other dimensions. So later on, we're going to it'll be a bit of a headache for you later down the line to see this, but you still do need. So you see that these dimensions line up. So wait, 3 is not equal to 5. Yeah. So I think it needs to be like 3, 5. I think this works. I'm actually hitting the realm of stuff that I don't have to do very often. Yeah, that does work though. Okay, so you need to have all besides one dimensions matching on both of them. If you want to justify this to yourself geometrically, you can try. You think about 3D blocks, they need to be able to line up such that you end up with only one thing different in each of them, and those end up to be the far sides of it. Yeah. So that's pretty fun, and yeah. What's the shape? Good question. Anyone want to guess? Is a 4x3x3x1. Yeah, weird, huh? Anyway, you can think on that and try to figure out why it is. This is more just showing you that there are some kind of interesting behaviors that you're going to have to deal with down the line. Cool. All right, I think that's that for coding section. And yeah. So basically, just one more thing. We're probably going to be able to actually let out a little bit early today. So you may have noticed that this class has a little bit of a different pace, a little bit of a different style, and a little bit of different stuff that I'm trying. That's not a coincidence. I'm still trying to figure out how to teach, because this is my first class actually teaching a real class. So I tried a pretty radically different thing today, and I want to do a poll on a few different things to see how people feel, one about this class in particular and more about the class as a whole. So give me a thumbs up or thumbs down. I'm going to say some things. Thumbs up if you agree, thumbs down if you disagree. Everyone understand? No one thumbed up. Okay, cool. All right. Sorry. There was/is enough time for homework 1. Oh, all right. Okay. I'm curious. Who started homework 1 before the weekend? Okay. Pretty hard correlation there. Okay. Okay. I don't want to call anyone out for not starting. I wasn't going to give anyone shit. You haven't started it yet? Cool. Nice volunteer. All right. Yeah. No, I do think that these homeworks are doable in a pretty short timeline. I know that that's not exactly the same as they are reasonably doable quickly. I'm still trying to figure it out. If you end up thinking that the homeworks are way too hard or way too frequent or whatever, let me know. I'm really open to advice here. Again, don't want to riot, so please just talk to me instead. Okay, cool. So enough. I want the lectures to focus on more implementations and details. Okay. Versus ideas and theories and like more broad stuff. Okay. Seems majority yes on that one. Okay. There'll be plenty of other stuff too. This was a little bit harder on the side of details and stuff than I will normally go. Just wanted to give you an extreme example so people could compare it. All right. And I wish the lectures were slower and covered less material. All right. Okay. That's what I like to see. Okay. Cool. Yeah. No, there's plenty of material. I want to go through it quickly. I'm just afraid of a little bit of a like Barrington situation, you know. All right. And there are too many quizzes / Kahoots. Okay. I think part of my soul wanted you guys to say, yeah, stop doing that because they're a ton of work. But okay, no, I'm glad to see you guys enjoy it. I am planning, my tentative plan is to have either a Kahoot or a quiz every class. I'm not going to hold myself to that because, again, like I said, it's a lot of work to come up with good questions. But that's sort of the idea because I want to have a break in the middle of class. This one, I think probably I did get a feeling of was too much all at once. People got bored halfway through. I try to avoid that by having a little treat right in the middle, something fun. Okay, cool. And last one. The homework was actually fun, and I learned a lot from it. It's fine for you to say no on this if you're feeling that, by the way. Yeah, I will. In a second, I'm going to open up to just suggestions and stuff also because we have a bit of time. Okay, I think I'll probably take an 80% hit rate on the fun and learned. I guess that's okay. I'll need more data.
Just maybe another homework and I'll have a strong opinion.
Okay, fair enough. All right, so now I'm going to open it up a little bit to suggestions that people have. I mean, we have a little bit of time. Yeah, hands right up. Okay, cool. Yeah.
All the homework's going to be like this much math?
No, actually. So probably this one was probably the most math you're going to get for a long time. Your suggestion is less math?
It's disappeared now.
Your suggestion is no more math for the rest of class. I don't think you can totally avoid it for machine learning. I mean, I think you guys will agree that for this first homework, this math was necessary. It was the math that you had to do the project. I couldn't get out of it. Not that I hate math. I was a math major. But still, I do think that it's better to not have a lot of math on these because the fun part is doing the machine learning. Okay. Suggestion?
Yeah, so on the CSV and the homework, I saw just a bunch of random data points.
Yeah.
Just like to see what those attributes actually are.
So I hid those on purpose. And I will tell you why on Wednesday. Yeah. It's ominous, right? Yeah. But there's a reason that I hid those attributes. Okay. Anyone else have any suggestions? I mean, I'm very open to it. Yeah.
Are there maybe you could find additional readings or some kind of course note thing that can
That's true. That's yeah. I think I am actually probably supposed to supply course notes. I think. How about this? If anyone is willing to be a course note taker, to be honest, I don't know if I have the time to do it. Not I'm probably the best person to do it, but it's hard. So if anyone wants to volunteer to take course notes, I've seen some of you take really good notes. If you want to do that, then hit me up. I don't know what I can offer you. Yeah. I don't know if it's allowed for me to offer you extra credit or not, so I'm probably not going to for now, but maybe, I don't know. Yeah.
I think my suggestion was leaning more towards a substitution for a textbook or something.
No, I know. So like, there's a lot of stuff online, and I can definitely link online resources and stuff. You sort of just reminded me that I think I have to do that. Yeah, I can link resources. I'll even ask the TAs, I think, to get some stuff together. YouTube videos, I think, are actually probably the top resource in my opinion. There are textbooks and stuff, but like 3 Blue 1 Brown has some really good videos on backpropagation. And if you really just go onto YouTube and Google machine learning, there's a million videos that are all really good. Anyway, I'll get some resources though. All right, any more suggestions? I'm going to take no suggestions means I'm doing 100% a perfect job, right? Okay, cool. So next class I think will be a little bit less. This, a little bit more new material. We're going to be doing multi-layer perceptrons and/or real neural networks next class. So get ready for that. And I'll see you then. Bye. Oh, yeah.
Like, I saw many people post the gradient, you get like 100, 200, 300, 400, like for the steps. Like, do you know why that's occurring?
Like when the learning rate really high?
No, like when you do this, like when you get the graph, you get like the number of training steps. Like,
yeah.
Is that fine? Or is it?
Yeah, that's fine.
Okay.
So, yeah, I'm not 100% sure why.
Put like a valid answer. Some people are saying no, it has to be going by increments of 5. Like some.
No, it should actually be like that. I think there's a difference. I think it's fine. It's fine. Yeah.
Really quickly, I was wondering if I could get an extension for the homework. Just transferred in.
Yeah. So we have a form on Moodle for that sort of thing. Just fill out the form. I'd say basically take as few extra days as you possibly can, and I'll warn you. So like, if it gets to the point where like you don't think you can finish homework 2 and homework 1, probably just do homework 2 and let me know in the form, and it should be okay.
When is homework 1?
Homework 1 is due tomorrow.
Tomorrow? Okay, no.
Tomorrow at midnight. But the truth is that homework 2 relies on you knowing stuff from homework 1. So it's possible really to skip it. I'll try that. Never know where. Nope, not this. That's super cringe.
I just put the camera back on.
It doesn't turn off the tabletop. Oh well.